Okay, thank you very much. Let's start. So, Dobre dzień. I said it right? Oh, it's a top that I can do. We need to talk in English. So, my name is Avi Alkobi. I am the technical director in Linux Technologies, responsible for the networking product line, basically the switch. And today we're going to talk about something which we think in Mellanox is very important, the telemetry aspects. Everybody, maybe I'll start with the question, who here knows about Mellanox, heard about Mellanox? Okay, that's pretty good. So when you heard about Mellanox, what is the first thing that you are thinking of? High performance, probably? Yeah? Open system, yeah, that's right. But I waited for this answer. Okay. Okay, so we'll skip the NVIDIA part because I didn't have time to change the logos. But yeah, so Mellanox is really known, I think, in the world in the high performance computing aspects, providing performance to the network, high performance. All these topics I will not talk about in this session. I will strictly talk about telemetry and visibility. So a bit about Mellanox. Mellanox is near 3,000 people company, headquartered in Israel and Sunnyvale, California. I'm coming from Israel. Very happy to be here in Warsaw, great city. And before talking about telemetry, I think it's important for us to understand where I'm going through to this in this presentation, to also know where I'm coming from. So Mellanox technology has a unique value, added value to the market. It's basically kind of the only company in the world that is doing end-to-end networking. What I mean by that is that PCI to PCI, if it's server to server, storage to server, all the network components are actually designed, manufactured by Mellanox. So we are doing NIC cards, which are attached to the server, to the storage. We're doing the cables. We're doing the switch, cable, NIC card. And not only that, every component that you will choose, let's take the switch, for example. We're doing it end-to-end vertically. It means that we're doing the chip inside that powers the switch itself, the ASIC, the bits and bytes, and then software, and then even management software to manage the entire fabric. Having said that, another value of Mellanox is that we are totally open. We're actually very active in the open Ethernet community. It means that nothing is locked, no feature fees. You actually can run different operating systems on top of our switches. So if we are totally open, and actually most of our deployments are with our NIC cards, other switches, our switches with other NIC cards, cables and so on, what's so important about this picture? And how is that related to our story here, which is telemetry? It's important because Mellanox, because we are designing all the parts, all the components down to the chip itself, we have a special vision about what needs to be done in this pipeline, including the NIC, including the cable, including the switch, to make sure, first, that you will get the best performance. If you bought 100 gigabit, you will actually get 100 gigabit out of it. Sounds kind of, obvious? No, it's not. You can buy 100 gigabit, doesn't mean that you will run 100 gigabit or 200 or 400 or 25 even. And the second thing is that we are looking at the network, not only this part, but the network, and thinking about how you can get more visibility into it. So what is the telemetry? This is a definition from Wiki, to summarize a bunch of components that will communicate some information to a centralized location, which will kind of present the status of your network in this case. Telemetry doesn't have to be so complicated, so high, end. Telemetry is definition that covers also SNMP, counters, logs, S-flow, things that everybody are doing. But we see that today, when we're looking at our network, SNMP counters doesn't cope anymore. We need something else. This is not Mellanox saying. This is the industry showing clearly. And why is that? Where we are looking on the scale-out networking, and scale-out networking has many names. You can call it scale-out, you can call it pay-as-you-grow. leaf spine, the same idea. Taking one use of switches, connecting them in this kind of class, leaf spine design, and then there are only added values for scale out versus what we call scale up, the C solution, the 3-tier solution. That was the legacy solutions. Only added values. I will not name them right now. So only values, but one thing that is happening is that things are getting more complex, right? So if you have, for example, tunnels, XLAN, virtualization, then your traffic pattern, which is east-west, is getting more complex. You need to have more information about it. And I'm not even talking about adding more features like RoCE, RDMA over Converged Ethernet, which will boost your performance, but again, will add more complexity. Now I need to define something. It's not about the complexity of the control plane. Actually, it's different. If you see the big boys, our competition, Microsoft, Facebook, and others. Let's take Microsoft, for example, big customer of ours. You know what they are running in their Azure cloud data center? They are running BGP. That's it. Down to the host, from the highest levels of spines, the super spines, down to the host itself, it's basic layer 3 BGP. Okay? So on the control plane, you see the graph, less and less features. This is the Cisco way, millions of features. This is the Mellanox way, basically BGP, EVPN, VXLAN EVPN, with partnering with companies like Cumulus and others that are doing it very well. So even VXLAN is basically MPBGP. It's BGP that is learning a new type of addressing, which is called EVPN. So on the control plane, it's very simple to build this leaf spine scale out, but on the other hand, you see what happens on the telemetry side, more and more features to understand really what's going on in your network. So why do we need telemetry in the first place? So the first one and most important one is the improved time for innocence. In simple words, if I am a network administrator, for me telemetry is basically to say, this is not my fault. This is not network, go to the other guys, other teams, right? It sounds a bit funny, right, to say that it's not me. But actually, this is the first reason, you know, to have better visibility into the network and say, okay, this is not the network reason, this is not the network problem, and if it is a problem, then the second is really understand what is the problem very quickly. And also, the third one is actually, if I got a gear which I expect to perform in some way, and it does not, I need to understand why not. Two types of kind of telemetry which I'm going to mention today, in-band telemetry, and another one which is called What Just Happened, which is unique for Mellanox. I will start with the in-band telemetry part. So what is in-band telemetry? This is a very advanced way to do telemetry. It means that basically the traffic that is running over the network, the traffic itself, will provide me some information. I will collect the traffic, analyze it, do some stuff with it, basically do machine learning, okay, deep learning on the traffic that is running on my network and get some conclusion about what's happening there. What just happened is a different topic, which I will talk about more later. I would say that what just happened is totally different. It's not about collecting all the data. It's actually providing the reason from a single packet. So let's start with in-band telemetry. And by the way, they are not contradicting each other, they're actually completing each other. They're not competing. So if you're looking on our network, these leaf spines, packets are going through the network. And in-band telemetry basically means that I'm using the actual packet, not packets that we're injecting for telemetry. The actual traffic, the customer traffic that is running over the network will be stamped in every device with some data. This data eventually, when the packet goes through the entire network down to the end of the road, will also be collected by kind of a big data machine that will collect the actual data, the actual packets, including all the timestamps and other stamps of data that were stamped along the way, along the switches, and by that, do some deep learning and get to some conclusion. And this stamping of data over each of the devices This is an operation that is made by the silicon of the switch. This is not software. You cannot do that by software. It has to be hardware that is doing it. This is an example of our chipset. It's called Spectrum 2. This is our newest chipset, the 6.4 terabit ASIC that is capable to do from 1 gigabit Ethernet up to 100, 200, and 400 gigabit Ethernet. And it has some values which differentiate us from other vendors because we are doing our own ASIC. It has a very good buffer architecture. It has a very good virtualization aspect, VXLAN, tunneling, and other things. It has many other values, and one of those is telemetry. So for a chip inside a device like a switch to do this telemetry operation, to stamp the packets with more information, you cannot work with what we call legacy fixed pipeline. So if you take a switch, it has a pipeline. The packet that goes through the switch will go through a component called Parser, which will extract some information from the header of the packet, which will be used later on the pipeline. Then you are doing some bridging, maybe tunneling, routing, then queues, buffers, and then out. This is kind of the flow of a packet on a switch. But to do telemetry, first of all, you need a flexible parser. It's not like, in legacy parser when you know what you are going to collect, like MAC address, maybe IP, maybe TCP port, maybe more headers you need. You also need it to be flexible. This is an example of how it's been done. So we're taking the actual packet and adding a payload. This is a template. And on the template, you have some holes. This will be the places where on the pipeline, the ASIC will add some information. For example, a timestamp for latency. For example, some reason that something happened to the packet, okay? Around the bridging, routing, different phase of the switch itself. And eventually, all this packet needs to move through the switch in a speed that is a switch speed. That means, for example, in this ASIC, 9.54 billion packets per second. This is the speed of a switch that is doing 400 gigabit, and it's not losing any packet, okay? So this is a hardware operation. And eventually all this data will go to a big machine, a big data machine, and it will crunch the data, the actual data, and learn something from it. So obviously, I will not be able to take all the traffic, every packet, and move it to this machine because I will need a huge database, right? So I'm going to sample it. How much I'm going to sample it will be 1,000 packets, every 1,000, every 1 million. I don't know. It's not my decision, but obviously you understand that it means that if you're sampling too low, then maybe you will not have all information. If you're sampling too high, you have a huge database. And this costs a lot, by the way. This is very, very expensive. So going back to this picture, this is how in-band telemetry works. What just happened is touching another aspect. And this is kind of a graph that describes how we can actually take telemetry and show it in 2 dimensions. So there is the control plane and data plane. Let's start with that. Control plane means how my BGP behaves. Okay, how is the configuration working, MTU and so on. There are great tools out there, Arista, Apstra, AOS. Also Arista, they have a great solution. Cumulus Networks with a tool called NetQ. And other ones, those are some logos that I put it here. Okay, those machines, those tools, software tools, knows to do it best. And there is also the data plane. That means the actual data that is running over the network. We talked about in-band telemetry, and there are other companies that are doing it also. And then you can divide it by normal traffic and anomalies. So normal traffic means that the packet went from one side, got to the other side. It just happened, and then to learn how it behaved. What happens, for example, if the packet is dropped for some reason? In the switch, just dropped, what we call discard. What happened then? Then if you are doing in-band telemetry, it's going to be very tough because you need to be lucky. You need to sample the actual traffic, the actual packet that was dropped. And if you didn't, you lost it, right? So in this case, I would like to present something that's called what just happened. What just happened means that, and let's take, for example, the anomaly, which is a dropped packet. If I'm dropping a packet, the ASIC itself will know that he dropped the packet, so he will send information to the operating system, to the software. And from there, some kind of a database, it could be Redis, InfluxDB, and from there, it will be shown in kind of a software, can be GUI, platform that will actually present this data. One of those will be Neo, which is our own management system, fabric level management system. Later on, maybe Abstra, NetQ of Cumulus, and also all the standard APIs that are on there, Kibana, Grafana, everything that rhymes with banana. So there are many tools out there that can present this data. But again, this data eventually comes from here, from the chip itself. Okay, it actually knows I dropped a packet. Here is why I did it. Basically, we are covering the 5 W's, we call them. So why the packet was dropped, when it was dropped, where it was dropped, and yeah, the other ones. So if you have all the 5, you actually can basically provide the root cause and even a solution. So it can be dropped packet because of layer 1, bad CRC, flaky cable. It can be for layer 2 reason, layer 3, buffer, drop it because the buffer was full. ACL, let's say someone from my team just configured that every packet that is coming from this source IP needs to be dropped. He did a mistake, but I don't understand what's happening in my network. I'm not getting traffic from some reason. This is another reason. And also, it doesn't have to be packet drop. It can be packet that is not dropped. For example, congestions issues, latency, route validation, load balancing issues on the switch itself. For all those reasons, you don't need to collect all this huge data like Demand Telemetry is doing, but actually the ASIC itself can tell you this is the reason. And eventually it will be shown, this is the GUI of the switch, the device itself. So you will see a list in 24 p.m. in interface 1/9, a packet from this source IP to this destination IP was dropped. Why? Because VLAN mismatching tagging. One reason. Also in the CLI, recently in history, this is the CLI of our operating system. It's called Onyx. Actually, the ASIC doesn't only provide information about the packet, it actually provides the packet. Not the entire payload, the data, that's not important. The header of the packet. And then it's actually creating a pickup file. Pickup file is a TCP IP dump file, which you can actually show in the Wireshark can do a deep dive into debugging on these specific packets like you see here. And this is on the device itself, and eventually, as I said, kind of a fabric manager will take all the data from all the switches and present this data. This can be done by Neo, for example, by other tools as well, but also by Neo. Neo is our own operating system, is monitoring and provisioning the entire fabric, and also doing what just happened. So this is a snapshot from the GUI of the Neo, where you see a collection of all the switches in the network, the drop reason, and then sub-reason. For example, tunneling, and the reason why, or the reason why the packet was dropped. So this is a demo. It's a video demo. It's not a live demo. It's just safer. You see here a situation where there are two ESX. This is a VMware environment connected by Mellanox network, and there is a problem. The traffic is not running between ESX1 and ESX2, between those two VMs that are raising on top of them. This is the CLI. We're doing just show LDP to see where those VMs are connected to. So 1/21, 1/22 on the port, on the switch itself. If you are doing showing counters, you will see there are discards, 4 discards. Okay, so usually this is where we stop. Okay, there's just a counter of discard packet. This is what SNMP level will show you. If you are activating what just happened, you'll see that, okay, in 1/21, this is the port. there is VLAN 5, and you see that the VLAN is filtered. Okay? If you are running show switch port, you see immediately that the VLAN is not part of the trunk of this port, so you need to add it. Okay? This is a simple example of misconfiguration. And this is the GUI of the switch. So the same data also on the GUI, nothing special there. You can also filter it. You don't have to show all the information. For example, if you have a million packets dropped on the same port for the same reason, you will just see a counter and the reason. And also you have the pickup file, and you can download it and then put it on a Wireshark. And you actually have the actual packet. Think about how strong it is. This is something that usually is being done by mirroring. Okay, you need to mirror the traffic to actually get this data, and here you just get it from the switch itself. And then on the fabric level, in this case, we took Neo as an example. So this is Neo. You are pressing, yeah, it's a simple example, so you see only one reason, and then you see the same, value again, why the specific issue happened. VLAN filtering, and you have all sorts of filters, and this is a software thing. You can filter it and show it in different ways. Okay. That was about what just happened and in-band telemetry. Any questions? So today, in-band telemetry is something that all the vendors are doing, basically. For what just happened, yes, the capability that Mellanox provides through the ASIC. So as I said at the beginning, one of our values is that we are designing a switch system. One of our values is the ASIC inside is ours. It's called Spectrum or Spectrum 2. So yes, this is something that's coming from the ASIC. Regarding the software that is handling it, then yeah, today it's Onyx, our operating system, or Neo. NetQ, Cumulus tomorrow, Apstra very soon, I hope. We are working with them. And soon we're going to see more and more tools like Kibana, Grafana, and so on. Any other question? Are there any network administrators or people that are dealing with network here? Good. So I have a question. Did you have a situation where you came in the morning and you saw 100,000 packets were dropped for some discard packets, and you need to understand why? What didn't happen? All the time. Okay. So I came from the application engineering. This is something very common, and usually what happens is that you need to reproduce it somehow. And when you're reproducing it, usually if you need to really understand, probably you need to do span or mirroring to some server to actually learn what happened and why the packet were dropped. This is what just happened is solving. And again, this is a portion of all the in-band telemetry. It's not covering everything, okay? But we think it's an important portion.
More questions? In that case, thank you very much.
Thank you very much.